28. Let's start with 28 and see where we go. Now, 28, what I want you guys to see here is notice how it's starting out with a fraction with both numerator and denominator with addition. And then the last part ends up with multiplication. That means somewhere along the lines you had to have common denominators to do all of that. Okay? So what I'm going to do is rewrite the numerator and rewrite the denominator right off the bat in terms of sines and cosines as a complex fraction. I know. You'll be all right. So the numerator is 1 over cosine plus sine over cosine all over cosine over 1 plus cosine over sine. Are we okay with that?
Yeah.
So I'm going to work with each, the numerator and then the denominator, independently of one another to simplify. Okay? The numerator of 1 plus cosine plus sine over cosine, do they have a common denominator?
Yeah.
All right. So I'm going to rewrite that as 1 plus sine over cosine.
Yeah.
Okay? The bottom part, we'll get a common denominator by using it with sine. We okay with that?
Yeah.
So the bottom part, I have sine. So it'll be sine times cosine plus a cosine.
Because you gotta do like the times the.
Yeah, what is it missing? I'm doing the common denominator. The first one was missing the sine, the second one had it, so it's okay there. Are we okay on that?
Yes.
Okay. Now, what I'm going to do is I want you to see in the lower denominator. That numerator has sine times cosine plus a cosine. Can I factor cosine out of those two terms? By doing that, I get this. Cosine times sine plus 1 all over sine. Are you okay with that? All I did is I took these two cosines and brought them out. Okay? So now I have this disgusting looking complex fraction. I have 1 plus sine over cosine divided by cosine times the quantity sine plus 1 over sine. So I'm going to rewrite that horizontally before I flip anything. Remember, it's top divided by bottom. By rewriting that double fraction there, sometimes it's a little bit cleaner to see that following step. So we have 1 plus sine over cosine divided by cosine sine plus 1 all over sine. What happens now? I'm going to flip that second fraction, okay? So I'm going to flip that second fraction. Let's move this up. And what drops? The 1 plus sines.
Yeah.
Is it okay if it's 1 plus sine and sine plus 1?
Yeah.
It's the same thing. So sines drop, that part drops, and we wind up with sine over cosine squared, which is secant squared sine.
Why?
Yeah. How?
How? Sine over cosine squared isn't 1 over cosine squared secant squared when you move it up? Remember,
Oh, I gotcha.
Oh, duh, yeah, I got it.
That's when you split it apart.
yeah,
Oh,
okay.
makes sense.
So it's just bringing it back up. So that's where you get your sine, secant.
Is that probably
That
not?
makes sense.
Excuse me. That one's
It's quite tricky.
smidge.
Can we do 18?
Sure.
I don't know why I couldn't do that.
I couldn't figure it out either, so. I didn't know where to start.
I didn't take a long time.
Yeah. I thought 18 was so much.
Very kind of.
Don't start the way that I started earlier.
Why'd you do 16?
What happens sometimes is that if you start one way and you run into a dead end, then you're just kind of like, oh, man. So, did any of you guys start with this one by saying that cosecant squared was 1 plus cotangent squared? And then you ran into a dead end because you had the plus signs. Okay.
Yeah.
So, secant and cosecant are inverse functions, aren't they? Rewrite them in terms of sines and cosines. If you do that, you get sine squared over cosine squared. Or excuse me, just over cosine, sorry. You okay on that?
Yeah.
Sine squared can be rewritten as what in terms of cosine?
1 minus cosine squared. Then 1, and then you split them apart.
Then you split them apart, you're done.
Because it's 1 over cosine minus.
Yeah,
cosine
because now
squared
notice you've
cosine.
got that single piece in the denominator. In
Oh.
2 parts in the numerator, you can break it apart as their instead of being a common denominator, now you have 2 separate fractions.
Oh.
Yeah, and then things drop out and do that. So you could run into that brick wall of trying to Pythagorean identity that just doesn't work, and then,
Okay.
okay? 1 second, Phoebe, what do you got?
I was just wondering, for 16, was it okay that I did the right side?
Yes, I
I
do
did the right
apologize.
side down.
I do apologize, guys. I thought I mentioned that before you guys ran out the door. That is the only problem on this that I've ever seen that I've given you guys, that you have to go right to left. I promise you, everything that I give you on the test will say go, well, it's always going to be set up to go from left to right, okay? So don't worry, if you went from right to left, Phoebe, you're fine.
Wait, how did you do this first step?
Secant is 1 over cosine.
Yeah.
1 over cosecant squared is sine squared. All it is a reciprocal property there. What do you got? What, these things? Yes.
What was it?
Yes, ma'am.
30.
Third.
Same. Like 30.
Oh, that's another one of those nasty ones. Because you have to break them into multiple
Yes,
fractions.
then 30. Did I do 30
There'll
already?
be a few like this.
Yeah.
No, I didn't. I couldn't do 30. What was-
What happens in 30 is that you've got setups that don't have Pythagorean identity, and multiplying stuff out just looks like it would be awful to create squares and stuff. So try to do a complex fraction with sines and cosines. All right, similar to what we did in 28, I think. Try and do the same idea with the complex fraction. So the numerator becomes 1 plus 1 over cosine over sine over cosine plus sine over 1. Okay? Yes, Kate?
If you wanted to, could you split that up? Like cotangent was secant over secant.
No, because you have a plus sign in the middle. Okay. Now, in this one, get a common denominator for the top. We wind up with cosine plus 1 all over cosine. The bottom, you have a common denominator of cosine again. And it winds up being the same style problem we just did.
How'd you get those right?
I wouldn't make-
Common denominator would be cosine. This fraction needs a cosine, this one doesn't. This denominator has a cosine, this one doesn't. So you wind up doing the exact same thing that we did in number 28. Take the sign out.
And you go like right horizontal. then you go
Yeah,
up.
but like,
So now I have my top fraction is the cosine plus 1 over cosine. Then I flip the bottom one and I get cosine over sine times 1 plus
it
cosine.
doesn't matter if you flip the opposite ones, like if the cosine and the sine comes with this cosine at the top. Like I flipped the bottom part of the fraction.
Yeah, that's what I did.
No, I mean I flipped the top part, my bad.
Oh, don't do that.
Why?
It's because in order, remember when you're dividing, you're multiplying by a reciprocal.
Yeah, but
It just happens to be dumb luck that it worked. That's
Oh, I
all.
haven't checked it.
Sometimes it does happen, you get dumb luck problems that something like that could happen. Don't do that. You're always flipping the bottom part,
Okay.
okay? So now everybody see how everything just drops?
Yeah.
And you wind up with 1 over sine, which is cosecant. Sir? Same basic idea. In 24, both terms have tangent together. So since they share tangents, factor it out.
So we can make it sine squared.
So you get tangent squared times 1 minus sine squared. What's 1 minus sine squared?
Cosine squared.
Cosine squared. So now you have tangent squared, cosine squared, which is sine squared over cosine squared, times cosine squared, and then you're done.
Okay.
Can you go back on the next one?
Yeah.
I don't get 30. I didn't get there.
Which one?
30. Okay, I was fine.
Like,
I was fine.
letting it grab like extra stuff out of the bag and everything.
Okay. What happens in this part here, if it was 2 plus 2x, what do they have in common? If I factor out a 2, I get 1 plus x. It's the exact same thing. What do they have in common? Sine. I factored out what is left, 1 plus cosine. It's the exact same linear style property that we've used, but we're just using it via trig. The algebraic property doesn't change. Sir,
22.
double duck, quack, quack. You never played bingo?
What?
You guys ever play bingo?
Oh, okay.
I don't know
They-
double double.
I played.
When they say before, you have to say and after.
Oh.
Oh, I get it.
I-22, they would say, did you guys never play bingo with like grandma and grandpa?
Like you do now.
I have those, like,
If it's I-22,
Oh.
and they look like ducks,
Oh.
double duck, quack, quack.
Explain this in 6 seconds.
Yes.
I don't get it. I see it too with like.
See now?
I can kind of see it on this, but it looks like.
22, all I do is distribute.
I don't know. I see it.
22 distribute, but before I distribute, I'm going to rewrite my parentheses in terms of sine and cosine. Then you'll see right away how it drops. You have cosine times 1 over sine minus 1 over cosine. When you distribute in, you get cosine over sine minus cosine over cosine, which is cotangent.
I get it.
Okay.
Maybe you drew it. Can you do 36? Oh.
You have a dollar. I've helped you enough today.
Oh, see, has a question.
I have children to feed. They get hungry.
Oh,
36. In 36, it's another large common denominator style problem. Because in order to combine these two, you get the common denominator. You will notice that it looks like it's going to be awful, but if you write it out cleanly, it drops really fast. So if I'm going to add these two fractions together, I'd have to have the common denominator. My common denominator would be 1 minus cosine, 1 plus cosine. We okay with that? Numerator on the left needs a 1 plus cosine. Since I multiplied it by 1, I don't need to do anything. Numerator on the right needs a 1 minus cosine. Okay? Now, what is 1 plus cosine plus 1 minus cosine?
2.
Very good.
Over sine.
The denominator, you get 1 minus cosine squared, which is, you just said, Colin,
Sine squared.
which is 2 cosecant squared. Yes, ma'am.
Can we do 10?
Does that make it a little bit clearer? It looks like it's going to be awful, but it goes real quick.
Yeah.
We did this in class yesterday.
Oh.
And this kind of leads us into a couple examples I want to talk about today, as far as how we can use trig identities to help solve equations. In this case here, if I wanted to show that it equals, or cosine squared minus sine squared equals 1 minus 2 sine squared, that shows that cosine squared went away. You guys agree?
Yeah.
Which means they rewrote it in terms of sine squared. So cosine squared can be rewritten as,
1 minus sine squared,
so you have 1 minus sine squared minus sine squared,
which is 1 minus 2 sine
which is
squared.
1 minus 2 sine squared. That's exactly how that works. Okay? That's exactly how that works. That's fine. I want you guys to keep working on this. A lot of these things I don't want to take them out of your hands because there's so many problems in these that I want you guys to keep working. But I do want to show you a couple of examples of how you can use trig identities to solve equations. So it's kind of a mixture back of this 14.3 stuff and the 14.4, and how very easy it is to manipulate back and forth. For example, throw this one in your notes here. This is still, I've got a couple of these through the day. I don't have a good worksheet, if you will, with equations. I might just rely on you guys to write down a couple of problems to use this with. So let's say we have this, and I want to solve this equation for x. I want to solve this within one revolution and solve for x. And this is where things get a little messy.
So you have to write the x now?
Yeah, because we're doing the equation. We're not verifying or simplifying here, is it? We're going to solve the equation. That's why I put in that little bit of x is between 0 and 2 pi. We're going to solve that. We're find the value of x that makes this work. So what happens here is that I want you to see that you've got two different trig functions. When that happens, a lot of times, we're going to try and do, if it's not something that had like a sine times a cosine with the those you'd factor out a cosine. When it's just straightforward that you can't do much with, you try to create a Pythagorean identity. So here's what we do. I'm going to square both sides. When I square the left side, it's junk squared. Do you agree? So that's why I'm going to get junk times junk. So I have to FOIL it out. So I have 1 minus 2 cosine squared, or sorry, 1 minus 2 cosine x plus cosine squared of x, just by FOILing out.
It's not cosine x squared? It's cosine squared, right?
Yeah, it's cosine squared. Yep. Just like we were doing earlier. Okay. On the right side, it's a monomial. There's no addition sign between it, so you just square both parts. So what's the square root of 3 squared? And what's sine squared?
Squared.
So this is going to equal 3 sine squared.
X?
Thank you. Forgot. I'm doing an equation. I almost forgot. So now, take a look at what you have. You've got stuff on the left-hand side, that all in terms of cosines, and one lonely old sine squared on the right. What do you think you want to switch them all into? I want to go to cosine squared. I want to switch that sine squared to a cosine squared. That way it allows me to solve everything else out. I know that sine squared is equal to what?
1 minus
Cosine squared. So this becomes 3 times 1 minus cosine squared of x. So my right side of the equation becomes 3 minus 3 cosine squared x. My left side, are you guys okay if I rewrite it in descending order real fast?
Yeah.
I get that. What do you think you're going to do now? Add over a 3 cosine squared, and what do I do with that other 3? Subtract it, good. I'm going to add the 3 cosine squared. Oops. And subtract 3. Bless you. So what's 1 plus 3?
4. Good job, Paul. Yeah,
It's the easiest math problem we've had all day.
probably.
And now I have a trinomial set equal to 0.
You can take out 2.
Very good. Because the first rule of factoring is
GCF.
GCF. It also might be clean for you guys at this point to use that little trick of U substitution, just so it's a little bit cleaner if you want. You want me to do it that way?
Sure.
What that means again is instead of continually writing cosine squared x and cosine x, I'm going to let the letter U represent cosine of x. It's just going to make the trinomial look cleaner. That's all. Okay? That's all it does. So we get 4u squared minus 2u minus 2 is 0. And like Michael said a second ago, the first rule of factoring is always to find what? GCF. So if I take out a 2, since I'm setting it equal to 0, does that GCF of 2 have any bearing upon the problem whatsoever?
Nada.
And why is that?
There's no exponent with it. I got exponent.
Well,
Let me-
divide by 2.
It's one of those, isn't you're going to get a guess.
Where's the letter?
Because
Variable,
it's a
variable.
constant.
That's whatever. It's different.
It's a constant value that you just divide out, and it's okay. So now you go and ask yourself, what times what is negative 2? You add together to get negative 1. Negative 2 and 1. And I'm going to factor this by grouping like we've done so many times in the past. We have 2u squared minus 2u plus u minus 1. So you factor everything out. So do you mind if I slide this up some? Are we okay? I don't know if everybody's caught up
Yeah,
here.
we're okay.
Yeah. All right. So when you bring that up, then you have 2u plus 1 and u minus 1 equals 0. So now that you have your 2 separate terms set equal to 0, go ahead and put back in your cosine value and solve.
Oh, okay.
2 cosine of x plus 1 equals 0. Then the other one is just cosine of x minus 1 equals 0. So these are asking you, where is the cosine value? What angle has a cosine value of negative 1/2? And what has a cosine value of 1? Mike?
I got it.
Are we writing it in radians?
Yeah, just go right to radians in these, okay? So I know that the cosine value of negative 1/2 is cosine to negative third quadrant. Pi over 2, so let's see, that comes up, reference angle, adjacent to negative 1. 2, so that's, what is that, 60? So in this, that'll be a pi over 3 coming up, so that's 2 pi over 3? 2 pi over 3, and then it's also negative in the third quadrant, so what's that radian value?
Oh my gosh.
4 pi over 3. I don't have to worry about any revolution here because I asked you for just within that one full ringy dingy.
Sounds good.
And then where is cosine 1? Bless you.
Thanks.
Cosine is 1 at 0.
Wait, would that not
Is
be
it
a valid
what?
answer? So, oh, it can. Oh, it
It's
equals
because it includes 0 but not 2 pi. What's that? Correct. Because remember the parameter of the problem said it goes between 0,
Oh.
not including the 2 pi. That's all. Okay? So, in all honesty, it's really not that big of a deal. It just takes a little bit longer to go through because the only thing you have to realize is that you can utilize a trigonometric identity to make make it work. Okay? Yes, sir. Yeah. Oh no.
I mean, I'm at.
Mine took up half the page.
I'm at 14. Yeah.
It could be. Why not?
What's the other one?
We can only put two problems on the page.
You're surprised that I use this paper because I don't think I'm going to be able to
Makes you do what?
She wanted him to surprise us and let us.
Can I do another one real quick?
Yes, she did.
Yeah, that'd be like the best.
Yeah, but no.
I feel like you're like the most.
It's my birthday too, right?
Birthday was last night.
Bless you. I don't know, that was a sneeze cough, so whatever.
So does it matter which one?
Good question. Does it matter which one you switch?
No. So whatever one you like better.
Sure.
I like sine a little better. So.
All right, so you want to replace cosine with sine?
Yeah.
Okay.
Yeah.
Cosine squared is, how can you rewrite that then?
1 minus sine squared.
Perfect. So right off the bat, we're going to say that we have 1 minus sine squared x minus a sine squared x.
Is it
So 1
1?
minus 2.
What's that?
Oh, never mind.
Perfect. That's exactly right. You get 1 minus 2 sine squared x is 0.
Okay.
Do we like just
Yeah, I would.
do we
Same thing if you would. What do you think we're going to do?
Add and square.
Add?
No.
Wait, what can you turn into you?
We don't need to. This one you don't have to because you don't have a trinomial set up. Okay? In this case here, I could, is everybody okay with the idea that if I subtract
Yeah.
1, divide by -2, I get sine squared x is 1/2?
yeah. And then you
Wait, negative 1/2?
Yes.
Careful. What I'm doing here is I subtract the 1,
Yeah.
and then I divide by the -2,
Oh.
where I get the positive. You could add the sign and do that as well. Okay. So now, take your square root. So you have the sine value of x is going to be plus or minus 1 over root 2. Is it okay that I don't rationalize?
Yeah.
C.
So, what angle has a plus minus sine
45.
sine value of plus or minus 1 over root 2?
pi over 4.
Or 3 pi.
So sine value positive or negative pi over 4s.
Alright, so pi over 4.
It's all
Pi over 4.
perfect.
5
5 pi over 4. 7 pi over 4. Yeah. Let's go, baby.
Yeah. Yeah. That's it. Because, and you would have gotten the same result if you would have rewritten it in terms of cosine, because it works out the same. Because what do you know about sines and cosines at 45 degrees? It's the same. That's why it works. Because if you square, think about it. If you square root 2 over 2, and you subtract the square of root 2 over 2, what are you going to get? No. If you take, now listen, if you take root 2 over 2 and square it, and subtract root 2 over 2 and square it, what do you get? 0. Think about it. Junk squared minus the exact same junk squared. And 0 junk. It's gone.
It's gone.
I think I have
Yeah, but that's not, that's called grinding. I made it flat. That is kind of creative.
I'm gonna save this one smart for someone else.
I still was able to keep.
We'll do this also within one revolution.
I'm just gonna flip the page.
Oh, I have to look here.
If you look at this, which one do you think looks like it needs to be changed?
Secant.
Why?
Because
Guys, there's two tangent and only one.
Because there's other tangents involved. Okay? So when you see something like that, it's forcing you to move the secant squared. So secant squared is what?
1
Wait,
plus
wait.
tangent.
1 over cosine squared x.
Hold on.
Whoa.
We're right in terms of tangents, okay?
1 plus tangent squared.
So you have 2 tangent squared x minus 1 plus tangent squared.
Plus 3. Minus or equal.
Before I get to the other side there, notice why I threw that in parentheses.
You have to make it.
So you don't forget to distribute. Exactly, that thing. What? No!
Why not?
Seriously, you can wish in one hand and the other, see what fills up first.
Yeah, I did that experiment once.
How'd that work out for you?
Not very good.
It's kind of crappy, wasn't it?
I was
Funny. Distribute your negative. Two tangent squares and minus 1 for you. There's just a lot going on.
Yeah.
What rules tells you to distribute and everything like that?
Remember, secant, what I'm replacing with is just that secant squared of x. Secant squared of x is equal to 1 plus tangent squared. So when you substitute in for this, it just goes there, but remember the minus sign is still out front of it. So you have to remember that you have to distribute into both. Yeah, that'll go bad. And then nothing will work. Okay. Combine like terms on the left, you wind up, well, what's 2 minus 1?
1.
We have tangent squared x. What's negative 1 plus 3? Add the 2 tan, subtract the 1, and you get tangent squared x plus 2 tangent x plus 1.
What? Oh, it was just tan.
Do I need to worry about, can I use U substitution right here?
No.
Yeah, but do I really need to, you think?
No.
Think about what's asking here. What times what's 1? You add together to get 2.
2.
I don't know.
1 and 1.
1 and 1.
1 and 1, John.
So you get
1
tangent x plus 1 times tangent x plus 1.
So tangent is negative 1.
So
Where is tangent at -1?
where is tangent at negative 1? That's exactly it. Your x value is the inverse tangent of negative 1.
It will be in quadrants 2 and 4.
Quadrants 2 and 4, and
45 degrees.
2 and 4 at 45 degrees, so it's at
3 pi over 4 or 7 pi
7 pi over 4.
and that's how you use those. They're not. Yeah, exactly. I'm out! They're not. I mean, they look like they're going to be awful, but they're not that bad.
I think probably
Okay. What I want you to do. What's
It
that?
doesn't say verify you solved.
Yeah, I'll say solve. Okay. What I want you guys to work on here. Let's see this real quick. I want you guys to work on the back side of the sheet you guys were just doing.
Oh, I didn't even notice it.
Okay? Let's just do, let's do the 8 of them on the first 8 on the back.
So 1 through 8?
Yeah.
Okay.
But then I want you guys to try a couple of these equations. So in section 14.4,
Oh, wait, 1 through 8.
yeah, those are simplified, those are verified ones.
Okay.
But the ones that I want to look at as far as equations are concerned are on page 859, back in section 14.4.
Number 1 through 3.
Oh, would my note card go ahead with the problem numbers? I already worked, make sure they work. Oh darn, yes I will.
Do 2 and 4 odds.
2 and 4 odds, yes. No. Why did I put my note card with the problems on it? Oh, there it is. Ah,
What was it like, torture?
Oh, okay. Really boring.
Okay.
Number 27,000.
She said
A couple of them are just, they already have the same trig function built into them. I think there's only 2 of them that you actually have to switch some stuff around on to make it work. Okay? Bless you. I don't have the file up right. Give me a second, I'll get it. I'm not going to lie to you. The solving of the equation stuff with the trigonometric identity things, it's a little bit messy, but it is something that they do a ton of in pre-calc, because they use the trig identities to build into what are called double angle and half angle formulas. Okay? So the better you get at just quickly identifying sine squared as 1 minus cosine squared, quick little tricks like that, you guys are going to fly through trig next year. I'm not going to lie to you. Okay?
do this on the homework for next
Ooh, that's fine. All right.
Destiny, do you know for sure that's the case? We're not getting it. Oh,
Yeah, don't read anything then.
Uh-oh. Yeah, don't have
do I have to
to
Google it?
drop it. There's no 7.
If you guys want to get a picture of it, so you can get into it.
Oh,
Okay.
yeah, no, it's right.
It was, let me shut this off.
That's advertised.
Oh.
And that's
See him on the way to Johnson.